In this video, we'll begin our module on recursion by first talking a little bit about sequences and series in a more general setting. So most operations, such as the addition of numbers, are introduced as binary operations, which means we're taught that two numbers can be added together to give us a single number. But before long, we run into situations where more than two numbers should be added. For example, if four numbers, maybe we call them A1, A2, A3, and A4, are to be added, then there are several ways that we could write their sum. We could use parentheses, as you see here, to indicate that first we're going to add A1 with A2, next we're going to add A3, and finally we're going to add A4. Or first we could add A1 and A2, then we could add A3 with A4, and then add those two sums together. But we know that the results will be the same because the addition of numbers is what is called an associative operation. So essentially it doesn't matter if we group the terms like this. We actually don't need these parentheses at all. We could simply write A1 plus A2 plus A3 plus A4, and we're going to get the same answer no matter how we perform these additions. Another way of writing it is to use this notation, which will be called the summation notation. So we use the Greek letter capital sigma, and the variable k that you see at the bottom will be called the index. Then a sub k that you see here is called a general term of the series. So this will define which numbers are being added together in the series. And then we saw that we had, sometimes you'll see it written down to the side like this. It was k from 1 to n of ak. In this case, we're going to call 1 the initial index because this is where k begins. And we count up from 1, counting up by ones until we reach the terminal index n. Or you may also see this written below the sigma and above the sigma in this way. These are equivalent notations, whether it's written kind of here in front or on top and bottom. And we'll understand when we see this that this means we're going to add, and we're going to add terms which are indexed by the letter k. We're going to start wherever k starts, in this case 1, and we're going to count up by ones until we get to n. So let's see some examples of that, and you'll see right away that we don't have to use the letter k. We can use I or n or j. These are all common variables to use for an index. So the first example that we'll see is the sum. I is going from 1 to 4 of a sub I. Since the initial index is 1, our first term will be a sub 1. Then we're adding, because it's a sum, a sub 2, adding a sub 3, adding a sub 4, and then we stop because our terminal index was 4. So you can see that we counted up from 1 in terms of the index until we got to 4, and then we stopped. In the next example, you have a sum that's indexed by k, and k is from 0 to 5, and the general term is b sub k, so this will be b sub 0 plus b sub 1 plus b sub 2 plus b sub 3 plus b sub 4 plus b sub 5, and stop. And you could also have your index starting someplace other than 0 or 1. It could start at a negative number, as you see in the third example. We have I between negative 2 and 2. That means we'll take the term indexed by negative 2, and then negative 1, and then 0 and 1 and 2, just counting up from negative 2 to 2. Or you could also have an index that starts at some positive number other than 1. In general, the terms in our series will be more specific than in the first example. It won't just say a sub I or b sub k. You might actually have a formula for the terms. Like here, in the first example, this is going to be the sum, I going from 1 to 4, of I squared. So we're just going to take each of the integers between 1 and 4, square them, and add them up. So the initial index is 1. That gives us the term 1 squared. Then we add 2 squared. Then we add 3 squared. And then we add 4 squared. 4 was our terminal index, so we stop. And this, of course, is 1 plus 4 plus 9 plus 16. So that's 30. You may also have another example here is the general term is 2i minus 1, and I is being summed from 1 to 5, so that's 2 times 1 minus 1, plus 2 times 2 minus 1, plus 2 times 3 minus 1, plus 2 times 4 minus 1, plus 2 times 5 minus 1. When you simplify these, you get that the first term is 1, the second term is 3, the third term is 5, the fourth term is 7, the fifth term is 9, so altogether the sum is 25. Now this type of notation can be generalized to other operations. For example, we know how to find the union and intersection of 2 or maybe 3 sets, but we can generalize this notation, A1 intersected with A2 intersected with A3 intersected with A4. We could write it this way, where we're going to write our index, I equals 1 to 4, above and below the intersection sign, just like when we had capital sigma. So here are examples of how that would be written. This can be done for intersection, as you see here, union, also the Cartesian product, and the symmetric difference, all of which we learned in one of our first lectures on set operations. And so if you compare the left-hand side with the right-hand side, you can see that this notation is just much more compact and convenient to write, especially if you had many sets, like more than 4 or 5, say you had 10 or 20 or 100, it's going to be much more convenient to just use this notation. And this is going to work in a very similar fashion. Say we have 3 sets. In this example, we have A1 is the set 0, 2, 3, A2 is the set 1, 2, 3, 6, and A3 is the set -1, 0, 3, 9. Then if we take the intersection of A sub I, where our index I is running between 1 and 3, that's going to be A1 intersected with A2 intersected with A3. Again, in terms of these indices, we're starting at the initial index 1, and we're counting up by 1s until we get to the terminal index of 3. So if I took the intersection of these 3 sets, I'm going to look at their members, and I'm going to say, are there any members that are in all 3 of the sets? Well, what about 0? Is 0 in all 3 of the sets? No, because it's not in A2. Is 2 in all 3 of the sets? No, because it's not in A3. Is 3 in all 3 of the sets? It is. 3 is present in A1, in A2, and in A3, which means that this intersection is going to be singleton 3. We could also do their union, starting with the initial index of 1 and taking the union of all the sets, counting up in the indices until we get to the terminal index of 3. Then that would be just 0, 2, 3, union, 1, 2, 3, 6, union, -1, 0, 3, and 9. And that's going to be the set that just now includes all of their elements. But I know that when I'm talking about sets, if an element appears more than once, I only have to write it once. So this will be 0, 2, 3, 1, 6, -1, and 9. Exactly the same set we have above. We can also use this notation when we have expressions that have both intersections and unions. And it's very convenient to write these lengthy expressions in a compact form. So for example, this entire statement here, which says that A intersected with the union of B1, B2, all the way up to Bn, that's the same thing as first taking A intersected with B1, and then union, A intersected with B2, union, A intersected with B3, and all the way up to A intersected with Bn. This can be written more compactly here as the second line, which says that A intersected with this entire union, counting from 1 to n, of B sub i's, will be equal to the union of A intersected with each B sub I, counting from 1 to n. So we'll want to practice using this notation and get a little bit comfortable not only reading the notation and understanding what it means, but also being able to write such a notation on our own. Let's do some practice exercises. The following series. A, the sum I is from 1 to 3 of 2 plus 3i. That should be equal to 2 plus 3 times 1, since my initial index is 1. And it's summation, so I'll add, the next term will be 2 plus 3 times 2. And again, add 2 plus 3 times 3. And 3 is my terminal index, so now I can stop. If I simplify, this is 2 plus 3, so 5. The second term is 2 plus 6, which is 8. The third term is 2 plus 9, which is 11. So the sum is 24. For part B, I have the sum. I is running from -2 to +1 of I squared. So that's -2 squared. -2 is my initial index. Then I add, because it's a sum, and I'll just go up by 1. So the next integer is -1. I square it. Then I add 0 squared. Then I add 1 squared, and 1 is my terminal index, so I stop. So this will be 4 plus 1 plus 0 plus 1, which is 6. Part C, find the sum j goes from 0 to n of 2 to the j for n equals 1, 2, 3, and 4. So we're actually going to find this sum for multiple terminal indexes. So first, if my terminal index is 1, then my sum will be 2 to the 0 plus 2 to the 1, which is 1 plus 2, which is 3. If my terminal index is 2, then my sum will be 2 to the 0 plus 2 to the 1 plus 2 to the second power, or 2 squared, which is 1 plus 2 plus 4, and that's 7. If my terminal index is 3, then I'll have 2 to the 0 plus 2 to the first power plus 2 squared plus 2 cubed, which is 1 plus 2 plus 4 plus 8, and that's 15. And if my terminal index is 4, Then I have 2 to the 0 plus 2 to the 1 plus 2 squared plus 2 cubed plus 2 to the power 4, which is 1 plus 2 plus 4 plus 8 plus 16, and that's 31. So you can see as I'm going up, as my terminal index is increasing, I'm really just adding more terms. So all of these have the same first two terms. Then I added one more term and one more term. So there's a nice pattern here. Now for part D, we're going to do the same thing. We're going to be changing our terminal index. So let's say that our terminal index is 1. And for part D, we have the sum. K is going from 1 to 1 of 2k minus 1. So this will be 2 times 1 minus 1. And I just have one term in this case because the sum is from 1 to 1, starting at 1 and ending at 1. So this is 1. If n is equal to 2, then I start at 1, but I end at 2. So I have 2 times 1 minus 1 plus 2 times 2 minus 1, which is 1 plus 3, 4. If my terminal index is 3, then I have 2 times 1 minus 1 plus 2 times 2 minus 1 plus 2 times 3 minus 1, which is 1 plus 3 plus 5, and that's 9. And finally, if my terminal index is 4, then I have 2 times 1 minus 1 plus 2 times 2 minus 1 plus 2 times 3 minus 1 plus 2 times 4 minus 1. That's 1 plus 3 plus 5 plus 7, which is 16. And again, just as in example C, you can see that each of the successive sums that we computed contains, if you will, the previous sum, and then we're just adding another term. The next example asks us to express the formula without using summation notation. So the formula says we're taking the sum. I is going from the initial index of 1 to the terminal index of n of 1 over I times I plus 1. So if I start with 1, this should be 1 over, I'm going to put 1 for I and 1 plus 1, which is 2. Then I'll add the next term. Now my index is 2, so I'll put 2 for I and 2 plus 1, which is 3. And the next term I'll add. I is going to be 3, so I'll put 3 for I, and 3 plus 1 is 4. And I can keep going, just like this, until I got to, let's say I is n minus 1. Then I'll have 1 over, put n minus 1 for I, and n for I plus 1. And then the last index is n, so I'll put n for I and n plus 1 for I plus 1. And the formula says that this is going to be equal to n over n plus 1. So that's what the sum would look like if we didn't have the summation notation. Now we're asked to verify that this formula is true for n equals 3. Well, for n equals 3, I already have written my first 3 terms here. So I have 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4. which is 1/2 plus 1/6 plus 1/12. If I want to find a common denominator, then I can write this as 6/12 plus 2/12 plus 1/12. And when I add them together, I get 9/12. And that's, if I divide by 3 on top and bottom, 3/4. And since my n was 3, that's exactly n over n plus 1, just like the formula said it would be. So this is the verification that this is true when n equals 3. C says repeat parts A and B for the sum I from 1 to n of I cubed. So the sum 1 to n of I cubed should be 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed and dot 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 until we got to n minus 1 cubed plus n cubed. And the formula tells us that that should be equal to n squared times n plus 1 squared all over 4. Now let's verify this when n is equal to 3. So when n is equal to 3, then we have 1 cubed plus 2 cubed plus 3 cubed, which is 1 plus 8 plus 27, and that's 36. Now 36, I can think of as 36/1, and then multiply by 4 on top and bottom. So this is equal to 144/4. And 144 is equal to 9 times 16/4. 9 times 16 is 3 squared times 4 squared over 4. And since n was 3, that's exactly n squared times n plus 1 squared over 4, which is exactly what we wanted to verify. Okay, draw the Venn diagram for the intersection I is from 1 to 3 of A sub I. So I'll start with some universal set. Because I have an index from 1 to 3, I know that I have 3 total sets, A sub 1, A sub 2, and A sub 3. And I'll label them. Doesn't matter which one I'm labeling where. Now if I want to take the intersection of I running from 1 to 3, this would be the same as A1 intersect A2 intersect A3. So in the picture, that should be exactly this portion here at the center. Now, express in expanded format. So this is A union. I'm going to start my parenthesis, and the intersection of V sub I with the index I starting at 1. So V sub 1 intersecting V sub 2. And these indices are increasing by 1 all the way up till it stops B sub n minus 1 intersected B sub n. So that's the left-hand side. And that should be equal to, on the right, we'll have Again, the index starts at 1, so A union B sub 1. Whoops. Then intersection A union B sub 2, intersection A union B sub 3, intersection dot dot dot, intersection A union B sub n minus 1, intersection A union B sub n. So that's the expanded form. Now, for any positive integer k, let A sub k be the set of all x in the set of rational numbers such that k minus 1 is strictly less than x, is less than or equal to k, and we'll let B sub k be the set of all x in the rational numbers such that negative k is strictly less than x is less than k. So find the following unions and intersections. First we have union, index running from 1 to 5 of A sub I. So this should be A sub 1, which is the set of x in the rational numbers such that 0, because I plugged in 1 for k, so 1 minus 1 is 0, is strictly less than x, is less than or equal to 1. That's A sub 1. Then union, A sub 2, that will be x in the set of rational numbers such that 1 is less than x is less than or equal to 2. And so on. We'll have A sub 3 and A sub 4. I'm just going to put dot dot dot, union, and then the terminal index is A sub 5, so that's x in the set of rational numbers such that 4 is strictly less than x is less than or equal to 5. So this is the union that we want to find. Now if we think about these sets, they are disjoint. For example, let's compare A1 and A2. A1 is all the rational numbers up to and including 1, whereas A2 does not include 1, but it's every rational number larger than 1 until you get to 2. So because I'm doing the union, I'm collecting all of the elements. This should be those x in the set of rational numbers, starting at the lowest point, which is 0. 0 is strictly less than x. But then I have everything between 1 and 2, 2 and 3, 3 and 4, all the way up until 5. So because I'm taking the union, this is going to become the set of rational numbers between 0 and 5. Now let's look at part B. Part B, find the same union, but with the B sub k's. So this should be those x in the rational numbers such that negative 1 is less than x is less than 1. Union, those x in the rational numbers such that negative 2 is less than x is less than 2. Union, and again I'm going to just write dot dot dot. The last one is the x in the rational numbers such that negative 5 is less than x is less than 5. Now if we think about these sets, unlike the sets A sub k, these are not disjoint. In fact, these are nested, meaning that A sub 1 is a subset of A sub 2, and A sub 2 is a subset of A sub 3, and so on. So when I take their union, I'm just going to get the largest set, x in the rational numbers such that negative 5 is less than x is less than 5. This will be the union of all of them because it actually contains all of the other sets. Part C, we'll do the intersection for the A sub k's. So again, the same sets, the rational numbers such that 0 is less than x is less than or equal to 1, but now instead of union we're doing intersecting the rational numbers such that 1 is less than x is less than or equal to 2, and intersection dot 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 intersection the rational numbers such that 4 is less than x is less than or equal to 5. Now I mentioned when we did the union that these sets are disjoint. And we can see that because the first set, a sub 1, stops at 1 and it includes 1. So it includes all of the rational numbers from 0 to 1, including 1. Whereas the next set includes all of the rational numbers from 1 to 2, but it includes 2 and not 1. So because these sets are disjoint, no matter how many of them I intersect, I'm going to have an empty intersection. There's no overlap whatsoever. Let's look at D. D will be intersecting the sets B sub I. So this is first the x in the set of rational numbers such that negative 1 is less than x is less than 1. Instead of union, intersection, the rational numbers such that negative 2 is less than x is less than 1, x is less than 2, intersection, dot, dot, dot. The final intersection is with the set of x in the rational numbers such that negative 5 is less than x is less than 5. And like we said when we did the union, these are nesting outward, which is to say that b sub 1 is inside of b sub 2, which is inside of b sub 3, which is inside of b sub 4, which is inside of b sub 5. And that's why when we did the union, we said that the union would just be b sub 5. Now, since we're taking the intersection, this is actually going to end up being just the set b sub 1, because b sub 1 is contained inside all of them. So the set of rational numbers such that negative 1 is less than x is less than 1 is going to be this intersection. Now, in the last problem, we have introduced a new notation that wasn't explicitly talked about in the lecture. So this is, instead of summation notation, this will be product notation. It's going to be exactly like the summation notation, except we're multiplying instead of adding. And so the Greek letter that we're using here is pi, a capital pi, but the indexing is going to work exactly the same way. We'll have the general term here, the letter K is the index, and we'll have an initial index, in this case 0, a terminal index, in this case 3, but we'll be taking products instead of adding. So I'll show you that. So we just want to find these values. The first one is the product. The index k is running from 0 to 3 of 2 to the k, so this should be 2 to the 0, but instead of adding, we're multiplying. Multiplied with 2 to the 1, multiplied with 2 squared, multiplied with 2 cubed. So that's 1 times 2 times 4 times 8, and that's 64. We could also have something like in part B. Part B is asking us to take the product when the index k is running from 1 to 100. So that's a lot of terms. Let's just write out the first few and see what it looks like. So first I'm going to replace k by 1, and this is 1 over 1 plus 1. Then I'm multiplying by 2 over 2 plus 1, multiplying by 3 over 3 plus 1. And I'm going to continue this way until I get to 99 over 99 plus 1 and 100 over 100 plus 1. So if I rewrote that, that would be 1/2 times 2/3 times 3/4 dot dot dot. Finally, 99 over 100 times 100 over 101. And what I can see here is that I'm actually going to get a lot of cancellations. 2 will cancel with 2, 3 will cancel with 3, and I didn't write the next term, but the next term would be 4/5, so I know that 4 is going to cancel with that 4, and this is going to keep happening all the way down the line. Here I didn't write the previous term, but it should be 98 over 99. So 99 will cancel with the 99 that would be on the bottom here. 100 will cancel with 100. So all that's left is 1 over 101. So this example shows you that sometimes if you just write out the first few terms, maybe the last few terms, you can see a pattern going on and you don't actually have to write out the entire thing. And we can also see how convenient this notation is, because if I had to write out 100 terms, that would take a while, but instead I can express the same thing as just using this very, very compact notation. So this will conclude our lecture on sequences and series, which is our introduction to recursion. And in the next lecture, we'll discuss more about the idea of recursion.